Hello everyone, I hope you're having a lovely time of day wherever you are. Thank you for coming to tonight's invited talk. I'm very excited for this talk and I hope you are too. Thank you everyone for participating and watching the conference sessions today and earlier this week. I hope you enjoyed all the talks so far. For those of you who are joining us for the first time, the Student Symposium in Combinatorics is a conference for students by students, and it's an opportunity for us to share our combinatorics or combinatorics related research with other mathematicians around the world. Special thanks to our sponsors, Matrix, AMC, OSUMES, and UNSW School of Maths and Stats. We greatly appreciate your support. It's a great pleasure for me to introduce our speaker today, Aditya Ganguly. Adi is one of our special invited speakers, as he is a joint winner of the 2021 CMSA and Penfold Street Student Prize, which is a prize awarded for the best talk by a student at the Australasian Combinatorics Conference. So I first met Adi at the National Maths Summer School back in 2016, and I've been fortunate to have him in some of my honours classes at UNSW. Adi is the most lovely person, and he's always willing to help out with anything and everything. I see Adi around a lot, or virtually around a lot, literally everywhere at uni. He's involved in teaching, research, and outreach. So Adi's CMSA prize win is actually a really big achievement because he won the prize last year when he was an honours student. Also, he's the first person from New South Wales to win this prize since 2001. So the rest of us UNSW Combinatorics squad really need to up our game. Sorry. I've also heard a few stories about how Adi sometimes gives uni heart palpitations every so often, but we know he always pulls through and goes above and beyond our expectations. Adi is currently an honours student in software engineering here at UNSW under the supervision of Haris Aziz. His talk tonight is based on his research in his honours year under the supervision of Catherine Greenhill, working on random hypergraphs. I'm currently doing my honours with Catherine, and thanks to Adi, she now has ridiculously high expectations of me, so thanks for that. It's my great pleasure to hand over to Adi to talk about the existence of two factors in random uniform regular hypergraphs. Adi, all yours.
Thanks very much, Jodie. That was a really kind introduction, and from the sounds of it, you are much further along in your honours progress than I was at the same time. Okay, so let me get into my slides. Can you see that all okay? Cool. So yeah, today I'm going to be talking about my work during my thesis last year into proving the existence of two factors in random uniform regular hypergraphs. And I'm going to be saying those words a lot throughout the next half an hour or so. All right, so as you might guess, this talk is heavily about random hypergraphs, and that's a field that really grew out of random graph theory, which was developed by Erdős and Rényi in 1959, which is fairly recent when you think about graph theory having been around for the last couple of centuries. And at the time, they were really using random graphs just as a tool to find deterministic properties about graphs. But as we know now, random graphs are very, very interesting objects in their own right, and that's how we're going to be looking at them as well. And of course, hypergraphs are just a natural abstraction of graphs, and being abstract, they lend themselves to being used to model things from simplicio complexes to the neuron structure of the brain. And as you can see, there's some interesting articles about how it can contribute to the fundamental theory of physics as well. So it's a very interesting topic to explore and a very valuable generalization of graph theory. So our work in the thesis was to prove a new threshold result. So on one side of the threshold, what we're able to do is asymptotically, almost surely guarantee the existence of a particular spanning substructure called a two-factor in a random uniform regular hypergraph. And I'll get a little bit deeper into exactly what each of those terms are in a second. But first, a few preliminary definitions. So I'm sure most of you know, it's a combinatorics conference, so many of you know what graphs are, but a hypergraph is very similar. It's just a pair of vertices and edges. So the vertices you can think of, as with graphs, as just a finite set of dots. And edges, instead of being line segments or arcs between the dots, are now sort of bubbles that can include more than, that can include 2 or more dots at a time. So this here is an example of a simple hypergraph. And the reason that it's simple has to do with, well, the edge set has to in fact be a set. It can't be a multi-set, so you can't have any repeated edges. So you won't see any of the same bubble more than once. And you can't have any loops as well. So every single edge does in fact need to be a subset of the vertex set. You can't have a multi-subset of the vertex set as an edge. So what that means when I say no loops is you can't have a bubble that includes the same vertex more than once. You can't have an edge with the same vertex repeated. So that's what we mean by a simple hypergraph. And pretty much all the time when we refer to hypergraphs and graphs in the rest of the talk, we implicitly mean that they're simple, unless I mention otherwise, in which case I'll call it a multi-hypergraph. Right, so the other definitions I mentioned in the title, so uniformity, we say that a simple hypergraph is S uniform if every single edge in that hypergraph contains the same number of vertices, which of course has to be S. So this here, which you see, is an example of a 4 uniform hypergraph, because you can see that every single edge contains precisely 4 distinct vertices. And the most special case is, of course, a 2 uniform hypergraph, because that's just a graph. If every single edge has just 2 vertices in it, you can think of it as a graph. All right. So before I just mention the next couple of definitions, I might just point out that for a lot of these definitions, we just give the definitions as if they were for graphs, because it's exactly the same for hypergraphs, and especially the pictures as well. It's a lot easier to visualize it for graphs than it is for hypergraphs, but it's essentially the same definition. So a hypergraph is R regular if every single vertex has degree R. And by degree, we mean that the number of edges that are incident to that vertex. So you can count on this graph, which is the Peterson graph, that every single vertex has degree 3, so it's 3 regular. And this is also a cubic graph. It's a synonym for 3 regular. And now that we know what a regular graph is, we can also talk about regular spanning subgraphs. So of course, the Peterson graph was 3 regular, but it also includes something that we call a 1 factor, which is a 1 regular subgraph of the original graph that has to span the original vertex set. So you can see here that the 1 factor has to include every single vertex of the original graph. And in this 1 factor, each vertex has to have degree 1. And likewise for a k factor, it has to span the vertices of the original graph, and every single vertex has to have degree k. So the Pearson graph has a very notable 1 factor, and it also has a very notable 2 factor. And it's good if you keep the definition of 2 factors in mind, because that's what much of this talk's about, and that's what we investigate in more depth. So this one's a 2 factor because you can see, again, the subgraph is spanning, and every single vertex has degree 2. So this is one definition that isn't quite the same between graphs and hypergraphs, because cycles have to be defined a little bit more precisely for hypergraphs than they do for graphs. But luckily, we only have to worry about the case of loose cycles. So in a hypergraph, a loose I cycle is a cycle which has I edges, and any 2 consecutive edges have to overlap in precisely 1 vertex. So you can see here that this is what it looks like, and it's best to understand it pictorially because cycles, as I said, are a bit fiddly to describe formally. But this is an example of a loose 6 cycle, and of course the hypergraph here is 3 uniform because you can check every single edge includes 3 vertices. So you don't need to worry too much more about these, but they do come up in our proof later on. All right, so now that we know the basics of what we're talking about, let's think about some common questions that have been asked about regular graphs and, of course, regular hypergraphs. So one interesting property that's been debated for a long time regarding regular graphs is the relationship between 3 regular graphs and the property of Hamiltonicity. So Hamiltonicity is simply the property of a graph containing a Hamilton cycle, which is a cycle that includes every single vertex. So it's been investigated for a long time whether there is a special link between three regular graphs or cubic graphs and the property of Hamiltonicity. And of course, it's not the case that every single three regular graph is Hamiltonian, but it's been speculated whether every single polyhedral three regular graph is Hamiltonian, every single bipartite three regular graph is Hamiltonian. What about the combination of both those properties? If you have polyhedral and bipartite, does that imply that a three regular graph is Hamiltonian? And there's also a question at the bottom here, which is a bit different because it replaces this strong every condition with something a bit relaxed, which is almost all. And asks, are almost all three regular graphs Hamiltonian? So maybe let's investigate the answers to these questions. And it turns out that the first two answers are no. It's not the case that every polyhedral three regular graph is Hamiltonian, nor every bipartite three regular graph. And it's not interesting just for the fact that the answer is no, but also for the fact that it took, in the second case, the best part of 100 years to come up with that answer. So it turns out that even when you have sort of proofs by counterexample, it's not exactly easy to find these counterexamples to prove these negative results. And the third question there is even more difficult, apparently, because it's still open, and this is Barnett's conjecture. So we really don't know if every polyhedral and bipartite three regular graphs Hamiltonian. So these first three questions really serve to highlight just how difficult deterministic or even simple deterministic questions are about regular graphs satisfying certain nice properties like Hamiltonicity. So that sort of prompts us to ask, maybe instead of getting deterministic results, we can try and focus on random results. And that's where this fourth question comes in, which is, are almost all three regular graphs Hamiltonian? And the answer, thankfully, is yes. And it's yes, and we know that it's yes, because of something called the small subgraph conditioning method, which was a novel method developed by Robinson and Wormald in '92, precisely in order to answer this question. And we're going to investigate how they approach this question to understand this theorem. And just a footnote, it's a very appropriate theorem because small subgraph conditioning, that's SSC. So it's the perfect time to be talking about this. Right, so to understand that question in a little bit more depth, we need to get a good grip on what random hypergraphs are. And all it is a probability space over a certain set of hypergraphs. Now, if you think about all of the S uniform are regular hypergraphs on the vertex set of labeled vertices from 1 to n, that's a finite set of hypergraphs. So we can very easily turn that into a uniform probability space. So every single hypergraph is assigned the same probability. And anytime you draw a hypergraph randomly from that probability space, you call that a random S uniform R regular hypergraph. So technically it should be a uniformly random S uniform R regular hypergraph, but you can see why we'd rather use less words. And the special example is this probability space GNR2. And that's the uniform probability space of two regular hypergraphs, which are just graphs. R regular, two uniform hypergraphs. And yes, those are just graphs. So if we have a sequence of these probability spaces, and typically those sequences are defined by fixing R and S, and then letting n start from something small and then go up to infinity. So you get a sequence of these uniform probability spaces where the number of vertices is gradually increasing. And if an event occurs, we say that an event occurs asymptotically almost surely over that sequence of probability spaces if its probability converges to 1 as you increase n. So I want to stress that point, just that we fix R and S, and then we let n go to infinity. So we are always looking at a certain fixed R regular S uniform space of hypergraphs, but on a growing number of vertices. And that's the way we think about asymptotic results. All right, so let's return to that fourth question we had before, which is, are almost all cubic graphs Hamiltonian? And if we want to answer that question, let's just formalize it a little bit. let's define Hn to be a random variable that counts the number of Hamilton cycles in a randomly drawn, let's just stick with graphs for now, so randomly drawn graph from Gn32. So this is the space of cubic graphs on n vertices, or 3 regular graphs. Now, we can transform our question, which was, are almost all 3 regular graphs Hamiltonian, into this question, which says that as n goes to infinity, is it true that the probability that there is at least one Hamilton cycle, is it true that that probability goes to 1? And if that's the case, then it means that asymptotically, almost surely, there does exist a Hamilton cycle in a 3 regular graph. So if you don't have the small subgraph conditioning method, then the way you want to go about this probably is to try and get a lower bound on the probability that we're interested in. So that's the probability that we want. And the second moment method is a perfect way to, or is a good way to try and get a lower bound on that probability, because it relates this probability to the second and the first and second moments of the number of Hamilton cycles. So what Robinson and Wormald calculated back in 1992 is that the expectation of the number of Hamilton, or the expected number of Hamilton cycles is given by this, second moment's given by this. So plugging that into the second moment method, what that gives us is that approximately, asymptotically speaking, approximately 90% of all cubic graphs are Hamiltonian, which is good, but it doesn't really validate that suspicion we had that almost all cubic graphs are Hamiltonian. Remember, this is something that's been speculated for a long, long time. So the reason that it's not giving us the result that we want is because this lower bound is not going towards 1. So what we really need is that the variance of the number of Hamilton cycles, which is basically the difference between the second moment and the square of the first moment, we need that to become vanishingly small compared to the second moment as n goes to infinity. So that's what we need for the second moment method to give us the kind of results that we actually want. And that's apparently not happening at the moment. So if that doesn't happen, the trick that Robinson and Wormald came up with was that if you condition the variable you're interested in, Hn, on a particular event, you're able to bring the variance of Hn down dramatically. And it turns out that a really clever event to condition Hn on is the number of I cycles contained in the graph for varying values of I. So it turns out that if you know the number of not 1 cycles, but the number of 3 cycles, 4 cycles, 5 cycles, etc., in a graph, then that gives you a lot of information about how many Hamilton cycles are likely to be in that graph. And if you think about what we're doing here, we're conditioning on the counts of cycles of a fixed length. So in other words, that's small subgraph conditioning. So that's where this theorem gets its name from, because that's what we're doing. So let's get into now what our problem is. So moving on from the sort of genesis of the small subgraph conditioning method. And Robalewska proved that almost all random regular graphs contain a 2-factor. So what we want to do now is extend that result to the world of hypergraphs. So is it true that almost all R regular S-uniform hypergraphs do or do not contain a 2-factor? So it's a question we have to figure out the answer to. And it turns out that what we're going to find is that first we can find a sort of threshold point such that whenever R is less than that threshold, a random hypergraph does not contain a 2-factor. And whenever R is greater than that threshold, our random hypergraphs do contain a 2-factor asymptotically almost surely. So let's now try and formalize this question again. So let Y denote the number of 2 factors in a randomly drawn hypergraph that's R regular and S uniform on n vertices. And this is going to be the notation we use for the rest of the talk as well. So whenever you see Y, this is counting the number of 2 factors. And what we want to do is we want to ask, as n goes to infinity, is it true that the probability that Y is greater than 0 converges to 1? Or is it true that the probability that Y equals 0 converges to 1? So this first question is asking, does there asymptotically always exist a 2-factor? The second bit is asking, does there asymptotically always not exist a 2-factor? So the first approach to try and understand this problem is to try and get an upper bound on the probability that there does exist a two-factor. And we can do this by using Markov's inequality and first of all calculating the expected number of two factors in a random or regular S-uniform hypergraph. And in fact, when we did this, we did it slightly more generally, and we calculated the expected number of k factors in a randomly drawn hypergraph that's R regular and S uniform. So let me just step through quickly how we did that proof. And the idea is that if you want to calculate the expected number of k factors in a random R regular S uniform graph on n vertices, first of all, think about all the possible places where a k factor could be. So let's just take this example where we just have n vertices, and let's think about the case where s is equal to 2, just to make life easy. So let's look at graphs. This is an example of a possible k factor, well, in this case, it's a possible two factor for an R regular graph on 10 vertices. So as we saw before, the Peterson graph is an example of a 3 regular graph that does have this particular blue graph as a two factor. This is another example. So there are many different possibilities for what might be a k factor in a random R regular S uniform hypergraph. So if we want to count how many such k factors there are in a random R regular S uniform hypergraph, that's going to be a random variable in itself, and we can calculate the value of that random variable by first defining an indicator variable for each of the possible locations of a k factor. So what we want is that indicator variable takes the value of 1 precisely when your random R regular S uniform hypergraph does completely contain that given k factor g, and you want the indicator variable to be 0 otherwise. And in that case, the total number of k factors in your random R regular S uniform hypergraph is just the sum of all of the indicator variables. So the number of k factors is the sum of all the possible locations of a k factor of the indicator variable for that particular k factor. And now, because we want the expectation of the left-hand side, we take the expectation of both sides. And the expectation is linear, which is very nice. So we can take it inside the sum. And because this is an indicator variable, the expectation of the indicator variable is just the probability that it's equal to 1. And let's just remind ourselves that the event that the indicator variable is equal to 1 simply means the event that that given k factor is completely contained within a random R regular S uniform hypergraph. So that's the probability that we now need to calculate. Thankfully, what we find is that this probability actually happens to be the same no matter which k factor, which possible k factor g you're looking at. So in order to calculate this sum, all we need to do is calculate this probability for any particular k factor g, and then just multiply it by the number of possible k factors that you can have. So the way that we calculate that probability that we're interested in is with a corollary from Aldasari and Greenhill. And just a bit of background, the way that they came up with their formulas is working with something called the configuration or the pairing model, which comes way back from the likes of Boyle-Bush, relating to graph theory and random graph theory. But nonetheless, they come up with a formula which helps us find that this is the probability that we're interested in, quite a long formula. And likewise, they also have a formula for the number of locations that you can have a k factor, which is literally just the size of the number of possible k factors for S uniform hypergraphs on n vertices. And that turns out to be this. So then we just multiply those two numbers together, and we apply Stirling's approximation. And that tells us that asymptotically by the way, all of these results are asymptotic. And that tells us that asymptotically speaking, as n goes to infinity, the expected number of k factors in a random hypergraph from the space of hypergraphs that are R regular and S uniform on n vertices, that expected number is given by this formula here. Okay, so now let's just go back to our simpler case of dealing with two factors. So we just replace k with 2 now in this formula. And what we find is that the first moment of the number of two factors in a random R regular S uniform hypergraph, that's asymptotically given by this lovely formula here. And as you can see, the only part of this formula that depends on n is this red bracketed section here, which you can see is put to the power of n. So if we want to know, asymptotically speaking, whether the expected number of two factors in a random R regular S uniform hypergraph, whether that explodes off to infinity or whether that collapses to 0, all we need to figure out is whether this combinatorial expression here involving R and S, if that expression is below 1, then the expected number of two factors will be 0 asymptotically. If this number is above 1, then the expected number of two factors will go towards infinity. So we call this red expression here C of RS. And what we were able to find is that there exists a certain threshold value, which can be expressed in terms of S, such that if R is less than that threshold in S, then that combinatorial expression, CRS, that ends up being less than 1. So in other words, the expected number of two factors will go to 0. And if R is greater than that threshold in S, then the expected, then that combinatorial expression happens to be greater than 1. So the expected number of two factors will blow up to infinity. So that's great because we can now immediately start dealing with this former case when R is less than the threshold value in S. Because if that's the case, then we know that the expectation of Y converges to 0. But of course, by Markov's inequality, that bounds the probability that we're interested in, which is exactly this probability. Remember, this is the probability that there exists at least one two-factor in our random hypergraph. That bounds this probability from above, which means that asymptotically, we have to have that this probability goes to 0. So that's already the first half of our threshold result done. It tells us, in this case, whenever R is less than the threshold in S, we find that a random hypergraph, a random R regular S uniform hypergraph, asymptotically almost surely does not contain a two-factor. Right. Now, that's about as far as we can go without the small subgraph conditioning method. So let's get back to this lovely method, and I'll give you a little more of an overview. So we saw before that the second moment method isn't going to do exactly what we want it to do. It's not going to give a lower bound of 1. And that's because the variance of the random variable that we're studying, that is going to be greater than 0. And it's going to be something that is significant relative to the second moment. So that's where the small subgraph conditioning method comes in, and it's an analysis of variance technique that cleverly tries to condition Y on some other random variable that we understand well. Now, whenever you condition Y on some random variable, the law of total variance gives you that you can sort of decompose the total variance in Y into two things which statisticians might call the explained variance and the unexplained variance. So the explained variance is sort of the variance that can be explained by the conditioning. So for instance, if you're trying to investigate the variance in the amount that it rains over the year, you might think to try and condition amount that it rains each day over the year, you might try to condition that on the season that you're currently in. So of course, there are 4 possible categories for what season it could be. And the explained variance is the variance that you get between winter and summer, say. And of course, you would expect the amount that it rains in each of those 2 seasons to be quite different. But the unexplained variance would be the variance that you get within all the days that occur during winter. And that variance cannot be explained by the way that you have chosen to condition your random variable. But of course, what you would hope is that by conditioning on the seasons, you've reduced the unexplained variance, because within winter relative to over the whole year, there would be less variance in the amount that it's raining per day because the weather is more similar every single day. So our goal with the small subgraph conditioning method is to condition on the counts of these small subgraphs, which are small cycles. And ideally, if we know all of the small cycle counts, then all of the hypergraphs that fit within that category should have very, very, very similar numbers of two factors. And ideally, they would have identical numbers of two factors, because that would say that the unexplained variance is 0 after we've conditioned on the counts of small subgraphs. But the explained variance will be the variance that occurs between different categories of numbers of subgraphs. So between hypergraphs that have 3 4 cycles and 5 4 cycles, right? There'll be a certain variance between how many two factors each of those categories of hypergraphs have. So that's what the small subgraph conditioning method is trying to do. And just to recap, yes, it's trying to show that the unexplained variance is 0 if we are able to condition y cleverly enough. So let's get into the actual theorem now, and it's quite chunky, but I don't expect anyone to really read this. This is just a simplified version of the original theorem. But I'm just going to point out a few key parts of this theorem. So y is the same y as we've been dealing with all along, at least for our purposes. This is going to count the number of two factors in a random R-regular S-uniform hypergraph. And these xi's are going to represent the variables that we condition upon. In this case, because we're dealing with hypergraphs, those are going to be loose I cycles, because they're quite well understood. And we're hoping that by knowing how many loose I cycles are in a hypergraph, that'll tell us a lot about how many two factors are in that hypergraph. And then I can just draw your attention right to the end, because as you can see, this line at the end is precisely what we want. It says that the probability that there exists at least one two factor converges to 1 as n goes to infinity. So if we want to show that this is the case, which of course we do, all we need to do is we need to prove each of these four things, and then our result follows for free. So I don't want to go through all of these 4 points because they sort of recap the kind of broad theories that I was talking about earlier. But I just want to draw your attention a little bit to the 4th point here, because this 4th point is really the one that sums everything up. What this 4th point asserts is that all of the variance in y can be attributed to that explained variance. In other words, the variance that you get between hypergraphs that have different counts of small subgraphs or small cycles. So if this is the case, then that's what we can deduce. And all of this stuff earlier is sort of just prep work to getting there. Now, naturally, therefore, this is also by far and away, this is the hardest part of the proof. But let's jump straight from there to the easiest part of the proof, which is part 1. And what part 1 just says is that the subgraphs that we're conditioning on, so in our case, the counts of loose I cycles, they have to be asymptotically independent Poisson random variables. So let's quickly have a look at why that might be the case. And in fact, we're not going to even do that very much because this work has already been done for us. So as long as we choose xi to be the number of loose I cycles in a randomly drawn R-regular S-uniform hypergraph, then what Cooper et al. And Altman et al. Found is that they perfectly satisfy point 1. In other words, they are asymptotically independent Poisson, and they have this particular mean. Now, Cooper et al., in fact, they proved that result more generally just for cycles in hypergraphs. And then Altman et al. Came along and they showed that, well, asymptotically loose cycles and cycles actually behave very similarly. So that's the reason why we're only focusing on loose cycles. So that's that bit done already. So that's the first part of the theorem done, but the rest of the bullet points, unfortunately, a little bit more technical. They involve some generating functions and things like Laplace summation, which ends up being quite fiddly to try and prove. But happily, we were able to show over the last year that all of those conditions do hold. So using the small subgraph conditioning method, what we're able to conclude is exactly what it's the other half of that threshold result we were talking about before. It says that whenever R is greater than that threshold, expressed in terms of S, randomly drawn S-uniform R-regular hypergraph asymptotically almost surely does contain a two-factor. So that's good news. That's precisely what we wanted. And this, in combination with our earlier result, gives us the complete threshold result about the existence of two factors in asymptotically, asymptotically almost surely in R-regular S-uniform hypergraphs. So that's precisely what we set out to prove. And the last bit that I'm going to talk about is a little corollary of the small subgraph conditioning method that I didn't mention earlier. And it has to do with something called contiguity between probability spaces. So we say that two sequences of probability spaces are contiguous if every single asymptotically almost sure event in one of those spaces is also asymptotically almost sure in the other space. Now, this doesn't mean that every single event has the same probability in both spaces, but or in both sequences of spaces. But only the asymptotically almost sure events, they need to have the same sureness across both sequences of spaces. So you can think about contiguity as a form of asymptotic qualitative equivalence between probability spaces. Qualitative because it's not really about the probabilities of events, it's only about whether events do or don't occur asymptotically almost surely. So the reason that we need to know about contiguity is because it's a really nice corollary of the small subgraph conditioning method, that as long as all of those conditions hold, you also get this bonus fact. And this bonus fact says that if the small subgraph conditioning method holds in relation to this random variable y that we're studying, which is the number of two factors, then the uniform probability space of R regular S uniform hypergraphs, well, that ends up being contiguous to what we call the weighted probability space. And this weighted probability space is the probability space you get by taking the same underlying set as you had before, so the set of all R regular S uniform hypergraphs on n vertices. But instead of all of those hypergraphs having exactly the same probability, you weight their probabilities by the value of y for that particular hypergraph. In other words, a hypergraph that has more two factors will have a higher probability in this space. And then, of course, you have to normalize in order to make sure it's a probability space. So the question is, why is this useful and what does this new distribution actually look like? To answer that, we actually need to introduce something else now, which is to do with the union of two graphs or hypergraphs. So it's probably easiest if you just look at the pictures, but if you have two hypergraphs which are on the same vertex set, you take the union of them by simply taking the same vertices and the multi-set union of all of the edges. That's really important. So the result of a hypergraph union might be a multi-hypergraph. So as you can see here, in particular, if you look at this edge and this edge over here, they combine in a multi-set union so that the result has a double edge in that position. So that's the union of two hypergraphs. And the reason we need to know about the union of hypergraphs is to introduce something called superposition between probability spaces on hypergraphs. So say you have two probability spaces, both on the same underlying set of hypergraphs. You can construct the superposition space of those two original spaces by randomly sampling an element from each space and then taking the hypergraph union and discarding it if it's not a simple hypergraph. So take this as an example. Say you randomly sample this first graph from your probability space G and this second graph from your probability space H, and you're trying to figure out if the union has to go into your superposition space or not. Well, you take the union and you see that it's got a double edge here, so it's not simple. So that means that you discard this from your probability space. But in this instance, you have two hypergraphs that you've drawn randomly, and then you take their union. It does end up being a graph, so you accept that into your superposition space. And of course, the probabilities flow from the fact that you're randomly sampling from each of these two things. So that's how you get the probabilities in the superposition space. Right, so why is the superposition space important? Well, it's important because it turns out that the weighted space is exactly identical, at least the weighted space when you're weighting by the count of two factors, that is exactly identical to the superposition of the uniform probability space of R minus 2 regular hypergraphs, or S uniform, of course, and 2 regular hypergraphs. So what's the reason that this might be the case? Well, first of all, let's think about the underlying sets of the left and the right-hand side. The underlying set on the left-hand side, well, that's the same as the underlying set for the uniform probability space of R regular S uniform hypergraphs, which means it is the set of all R regular S uniform hypergraphs. And on the right-hand side, think about what it takes for an R-2 regular hypergraph and a 2 regular hypergraph to combine in terms of a graph union and not be rejected from the superposition space. It means that they must have had no overlapping edges, because if they had an overlapping edge, they would have become, that would have made it a multi-hypergraph in the superposition and it would have been rejected. So that means that if you start with a hypergraph from here, every single vertex has degree at R-2, and then you take the union with a 2 regular hypergraph. So each vertex gets 2 extra edges incident to it, so it becomes R regular. So every single vertex gets degree R. So that means that every single hypergraph from the right-hand side is also an R regular S uniform hypergraph on n vertices. And it's not too hard to see why you can get every single R regular S uniform hypergraph on n vertices in this way as well. So they have the same underlying set. And let's also check why they have the same probabilities on the left and the right-hand side. Well, on the left-hand side, of course, the probability of a hypergraph corresponds, is proportionate to the number of 2 factors it contains. But that's also kind of the same thing on the right-hand side, because if you think about the number of ways that you can randomly sample the same result hypergraph on this right-hand side, well, it depends on the number of 2 factors that our regular graph had, because that's how many times you would randomly sample something from over here, and then whatever the rest is from over here. So that means that the probability of getting a R regular hypergraph on the right-hand side also is proportionate to the number of 2 factors that it has. So these 2 things are not like, these are more than contiguous, they're actually exactly the same space. And what that means is that we can equate our original uniform probability space of R regular S uniform hypergraphs on n vertices. We can say that that is contiguous to the superposition of R-2 regular hypergraphs and 2 regular hypergraphs, both S uniform and on n vertices. But the important thing is that this only holds as long as the conditions of the small subgraph conditioning method hold. So that means that we need R to be greater than the threshold in S. So what that means is that you can continue taking another 2 factor off here as long as R-2 is still greater than the threshold in S, right? Because nothing else has changed. So we can keep doing this until the value of the regularity drops below the threshold in S. So as long as R minus 2 times some number of n minus 1, as long as that's greater than the threshold in S, we get that our original uniform probability space, that's contiguous to the superposition of 1 R minus 2m regular hypergraph space, uniform, a uniform space, superimposed with m lots of these 2 regular S uniform hypergraph spaces. That's really good because if we want to investigate just the asymptotically almost sure properties on the left-hand side, well, it's good enough to investigate the asymptotically almost sure properties on the right-hand side. So that's pretty much all of the results that we've come up with in the thesis. And to recap where we've come from and what's next, Cooper et al. In 1996, they proved a threshold result for the asymptotically almost sure existence of a perfect matching. So that's a 1 factor in a random uniform regular hypergraph. We've been able to do the same thing for 2 factors, and we've also built upon the existing contiguity arithmetic. So that contiguity arithmetic basically said was something where you could decompose an R regular hypergraph in terms of like an R-2 and a 2. So that's what that contiguity arithmetic refers to. And the next question is, what about general K factors? So we've already done a bit of the work by finding the expectation of the number of K factors, but of course there's a lot left to do to fill out the rest of the small subgraph conditioning method and see whether you can get similar results for all sorts of k-factors. And that's the end.
Thank you, Addy, for that great talk. We all please clap react to thank Addy.
Thanks very much. Thanks for listening.
We will now be taking questions. So if you have a question, please pop it in the Q&A and we will answer it. We'll give some people time to type. So while we wait for questions, I do have one question. So do you mind going back one slide?
Yeah.
You said the next question would be, what about general k-factors? What kind of challenges do you see in trying to prove it for general k-factors that might be different from just like two factors?
Yeah, that's a good question. And honestly, like in a lot of the work that we did with two factors, we sort of felt that a lot of this can be extended to k-factors, but maybe it needs slightly neater ways of doing the algebra. Because if I maybe skip back a few slides. Okay, so if you see here, this was the expected number of k-factors that we found in a random hypergraph. And it's got a few interesting looking terms in it. It's got some r factorials, some k factorials, all that kind of stuff. But of course, when you plug in your k's too, you get a much nicer combinatorial expression. So that's just one instance in which the analysis looks a little bit easier when you have a fixed number of, when you have a sort of known size of your factor. And the reason that's kind of important is because this area of sort of random graph theory, it's really interesting because it combines a lot of combinatorics with a lot of analysis as well, especially in some of the stuff that you need to do to prove that last bullet point of the small subgraph conditioning method. That's got some things like Laplace summation and stuff in it, which are pretty calculus heavy, and some terms that arise when you sort of have factorials and stuff sitting around, they may not be the easiest to analyze, especially with the methods that we had to analyze some of those functions. Like, I think I remember trying to prove that a certain function had a unique maximum, and the way I did that was sort of just like maple bashing and trying to prove that it's got a bunch of terms with squares in it and all that kind of stuff. And it was quite numerical in the end. So it'd be interesting to see if someone can extend that to the general case of k-factors.
Cool, we have a question from Jeremy in the chat. So Jeremy says, going off that question about generalizing, will that change what small graph you condition with? Or do you think you'll still stick with loose eye cycles?
Yeah, good question as well. So I don't think I've seen any instance of the small subgraph conditioning method being used where the graphs that you condition with are not cycles, or, I mean, for hypergraphs, I mean, for graphs, it's always cycles, as I've seen. And for hypergraphs, it's either cycles or loose eye cycles. And the only reason we're using the loose ones is because, honestly, they're just easier to work with when it comes to hypergraphs. It's much easier to explore the interactions between a loose eye cycle and whatever structure that you're working with, because a loose eye cycle has a much better defined structure. So it's just much, much easier to work with. And asymptotically, because it has the same properties as general cycles, there's really no reason to be using cycles in general. So yeah, I think there's a paper of Altman, Greenhill, Isaev, and I think Lang as well. So if you look into that one, that will explain exactly why loose eye cycles are just as valuable as eye cycles. Yeah, that's right. Yeah, Birch cycle. Yeah, general cycles, I just mean Birch cycles. But yeah, I don't think it's been explored yet whether you use any different types of subgraph. But at least for this particular question, I don't see any reason to really stray away from cycles.
So Afsane says, does it make sense to think about two factors for other types of cycles than those cycles? Would similar ideas to yours work, or do you think there would be big hurdles to overcome?
I think it would be more interesting to maybe explore, maybe to go back to the case, to sort of early small subgraph conditioning work for graph theory and see whether those results can be replicated using different small subgraphs rather than cycles. Like one of the reasons that cycles are so great is because they do satisfy the asymptotically independent Poisson random variables property. So you need to find, again, things that behave in a similar way. But I think just because that question hasn't really been explored at all, it would be better to go back to the case of graph theory and rather than hypergraphs, and see whether you can use more interesting subgraphs and maybe whether those can be used to prove any issues that or the existence of subgraphs that maybe haven't been able to be proved by the small subgraph conditioning method so far, although I'm not aware of any of those.
Cool. So last chance for anyone to ask questions. I don't think anyone has any more questions. So thank you so much, Addy. Could we all please join me in congratulating Addy by not reacting?
Thanks very much. And thanks, Jody. It's really, really well chaired and really nice introduction.